Today we're going to learn about the next exponent rule, which is called the power to a power rule. So when you are raising a power to another power, you are going to multiply the exponents. So if you look on your screen, the example there is 5 to the third power raised to the second power. This is a power to a power rule because you have a number being raised to a power, and then it's also being raised to another power. So to understand why we're multiplying the exponents, you have to understand what 5 to the third power means. 5 to the third power means that we're doing 5 times 5 times 5, or 5 times itself 3 times. This second power tells me to take this and to do this twice. So it wants me to do 5 times 5 times 5 2 times, or multiply this by itself. So I would multiply this by itself. And when I do that, I notice that I have 6 5s that are being multiplied together. That means if I wrote this in exponential notation, it would be 5 raised to the 6th power. Or the easier way to do this is when I have a power raised to another power, I know that I take this and I multiply, and 3 times 2 gives me an exponent of 6. So let's look at some examples. This example is 6 to the 4th power raised to the 2nd power. So in this problem, we are doing 6 to the 4th power to the 2nd power. And because I'm raising one power to another, I know that I can take this 4 and this 2 and I can multiply them. 4 times 2 would give me 8. So I would keep my base of 6 and I would have an exponent of 8. Again, you can always write this out. So I would write 6 to the 4th power, which means 6 multiplied by itself 4 times. And because that is being raised to the 2nd power, it wants me to take this and multiply it by itself twice. So I will write it again. And what I notice is that I have 8 6s being multiplied by themselves. So that is 6 to the 8th power. I can do the same thing for this, which is x to the 3rd raised to the 4th. Because it's a power raised to another power, I would multiply my exponents. So 3 times 4 would give me an exponent of 12. So I would keep my base of x and I would have an exponent of 12. Again, you can see how this works because if I have x to the 3rd power, that's 3 x's. This 4 is telling me to do this 4 times. So it wants 4 x of my x to the 3rd power being multiplied by each other. So there's a second one, there's a third one, and there's a fourth. And what I notice is that I have 12 total x's being multiplied by each other, which gives me x to the 12th power. For this problem, I have n to the 5th power raised to the 6th power. Because I notice that it's a power raised to a power, I'm going to do 5 times 6, and that's going to give me m to the 30th power. For this one, I have k to the 2nd raised to the 8th. So that means I have 2 k's, and I'm doing those 8 times. So that's 2 times 8, which is 16. So this will be k to the 16th power. Now, we can use these rules. So power to a power rules typically don't show up in simple problems like those. A lot of times they show up in more complicated problems like products or quotients. So a product, remember, is when you are multiplying. So in this problem that you see on your screen, you have 4 to the 3rd power, m to the 2nd power. This is considered a product because this is telling you to do 4 to the 3rd power and then multiply by m to the 2nd power. What you notice is that the product is in parentheses and the whole product is being raised to the 4th power. When you have a product or a quotient in parentheses, the rule is still the same. You are still going to take the exponents and multiply. So this would be 3 times 4, and then this one would be 2 times 4. And you have to make sure that you do this for each multiple in the problem. So again, to show why this works, this is telling you 4 to the 3rd power, which is 4 times 4 times 4. And then it says times m to the second power. So that's m times m. So that's what's in your parentheses. This 4 is telling us to take this and do this 4 times. So I'll do it 3 more times. So 4 times 4 times 4 times m. That's my second. Then 4 times 4 times 4 times m. That's my third. And then 4 times 4 times 4 times m. So that's my fourth. When I look at this, if I count my 4s, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that means I have 4 to the 12th power. When I count my m's, I have 1, 2, 3, 4, 5, 6, 7, 8. That would be m to the 8th power. Now I can write it out like this every time, or I can use my rule. And for each term in here, I'm going to use the power to a power rule. So for 4 to the 3rd raised to the 4th, I would do this 3 times this 4, and I would get the 12th power. For m to the 2nd raised to the 4th, I would do this 2 times this 4, and I would get m to the 8th. So whichever way I do it, I'm still going to get 4 to the 12th, m to the 8th. So let's look at some examples of this. This says 3 to the 3rd, a to the 2nd, to the 6th power. I'm going to take everything inside of my parentheses and raise it to the 6th power, which means I'm multiplying every exponent by this 6. So this has an exponent of 3, and I'm going to raise it to the 6th power. So I'll do 3 times 6 to give me 18. The base of this was 3, so I keep that 3 as my base. And because I did this 3 times this 6, I'm having a new exponent of 18. For a, I have an exponent of 2 being raised to the 6th power. So I'm going to do 2 times 6 to get 12, and I keep my base of a. So this is a to the 12th power. So the whole expression is going to be 3 to the 18th, a to the 12th. For this problem, I have 5 to the 7th, g to the 3rd, to the 4th. Every exponent is going to be raised to the 4th power, so I'm going to multiply every exponent. So this will be 7 times 4, which gives me 28. The base of 5 will stay, and I'll get 28 as my exponent. For g to the 3rd to the 4th, I'm going to do 3 times 4 to get 12. I keep my base of g, and now I have an exponent of 12. So my simplified solution is 5 to the 28th, g to the 12th. For this problem, I have 6 to the 7th, j, k to the 3rd, to the 2nd. I need to make sure I raise everything to that 2nd power. So I have 6 to the 2nd. So I'm going to take this exponent of 2 and raise to the 2nd by multiplying. 2 times 2 gives me 4, so I'm going to write 6 to the 4th power. Now, I cannot skip j. It looks like j doesn't have an exponent, but I remember that always means there's an invisible 1 here. So I'm going to take 1 and multiply by 2, which gives me 2. So now j is going to have an exponent of 2. And then k is going to has my exponent of 3 being raised to the 2nd power. So I'm going to do 3 times 2 to get 6. So I keep k, and now it's raised to the 6th power. And this is my simplified answer. For this one, 3f to the 3rd, g to the 2nd, all raised to the 5th power. Again, it looks like 3 doesn't have an exponent, but there is an invisible exponent of 1. So I will do 1 times 5 to get 5 as my new exponent. So I keep my base of 3, and now the exponent is 5. For f to the 3rd raised to the 5th, I'm going to do 3 times 5, which gives me 15. So this is going to be f to the 15th. For g to the 2nd raised to the 5th, I'm going to do 2 times 5 to give me 10. So this will be g to the 10th. Now the same applies when we have a quotient or a division problem. So everything in the quotient still has to be raised to that power. And so even though it's a quotient, you are still multiplying that power of 2. So this says x to the 4th over y to the 3rd to the 2nd power. Well, if I were to write this out, x to the 4th would be x times x times x times x. And y to the 3rd would be y times y times y. This second power tells me to take this and multiply it by itself. So I would multiply by another x times x times x times x and another y times y times y. Well, I know that when I'm multiplying with fractions, I'm just multiplying numerator times numerator and denominator times denominator. So I'm really just connecting all of this with a multiplication sign. What this means is that if I look in my numerator, I have 8 x's, or x to the 8th power. And in my denominator, I have 6 y's, or y to the 6th power. I can get that by looking in here and saying, okay, I have a power raised to another power, so I'm going to do 4 times 2 to get x to the 8th. And for this one, I have 3 raised to the 2nd power, so I'm going to do this 3 times this 2 to get y to the 6th. So let's look at some examples. This says 7b over c raised to the 2nd power. I need to remember that that 2nd power has to be done for every term. So if I'm doing 7b over c to the 2nd power, that's telling me to do 7b over c times 7b over c. What I notice here is that I have 2 7's multiplied by each other, 2 b's multiplied by each other, and 2 c's multiplied by each other. So that's 7 squared b squared over c squared, and that would be my solution. Now this makes sense because if you go back, each one of these has an invisible exponent of 1. So I would do 1 times 2 to get 7 to the 2nd, 1 times 2 to get b to the 2nd, 1 times 2 to get c to the 2nd. For this one, I have 5j to the 4th over k to the 7th. I'm going to multiply all of my exponents by this third. So I remember that 5 has an invisible exponent of 1. So I would do 1 times 3, and that gives me 5 to the 3rd power. Then I have j to the 4th to the 3rd. So that power to a power means I'm going to multiply 4 times 3, and I get j to the 12th. Then this is over k to the 7th to the 3rd. So I'm going to do 7 times 3 to get 21, and this is k to the 21st. So this is my solution. All right, for this one, I have 3 to the 3rd, x to the 4th, over x to the 5th, y to the 6th, and the whole thing is being raised to the 4th. So I can start this by taking all of my exponents and raising to the 4th power by multiplying. So this would be 3 times 4, which is 12. So I keep the base of 3, and now I have an exponent of 12. This one would be 4 times 4, so I would keep the base of x, and now I have an exponent of 16. Then that's over. Now for my x, I have 5 to the 4th, so it's 5 times 4, which is x to the 20th. And then I have y to the 6th to the 4th, so 6 times 4 is 24, so this is y to the 24th. Now if you look at this, you should remember this is a quotient. And what we've done with quotients before is we take these and we would simplify. So for right now, you can leave this like this, or you can take this and you can make it, if you notice that you have a like base here with x's. I can do 16 minus 20 to get x to the negative 4th power. Now, I'm not supposed to have negative exponents, so for right now, I can leave my problem like this. All right, for this last one, I have 2 to the 3rd, a to the 6th, b to the 3rd, over 2a to the 2nd, b, all raised to the 3rd power. So if I raise each of these exponents to the 3rd power, I have to make sure that I'm multiplying all my exponents by this 3. So this is 3 times 3, which gives me 2 to the 9th, 6 times 3, which gives me a to the 18th, 3 times 3, which gives me b to the 9th, over 2 has an invisible exponent of 1, so I do 1 times 3 to get 2 to the 3rd. Then this exponent of 2 times 3, so that's a to the 6th. B also has an invisible exponent of 1, so that's 1 times 3, which gives me b to the 3rd. Now, what I notice here is that I have all like bases in my numerator and denominator. So I'm going to remember my quotient rule, which says when I have like bases and they're being divided, I'm going to subtract my exponents. So in this one, I have another step that I can take. I'm going to take this 9 and subtract 3 because they both have a base of 2. So 9 minus 3 is 6. So that gives me 2 to the 6th power. For a, they both have a base of a. So I'm going to subtract their exponents, 18 minus 6, and get 12. So this would be a to the 12th. And for b, they both have a base of b. So I'm going to do 9 minus 3, which gives me b to the 6th. This is the most simplified answer.